Good morning, students. Today we are going to start the first chapter of organic chemistry of class 12. At the outset, I will suggest all of you to go through the organic chemistry part of class 11. This is because whatever has been taught in class 11 lays the foundation of the chapters that we are going to discuss in class 12. For example, organic reaction mechanism, chemistry of alkanes, alkenes, alkynes, Grignard reagent, Markovnikov's rule, anti-Markovnikov's rule, etc. etc. All these concepts will be required once again in a refurbished way. So, once you recap the organic chemistry part of class 11, it will be very convenient for us to take forward the subject. So now let us start with the first chapter of organic chemistry, that is alkyl and aryl halides. Now let us start with alkyl and aryl halides. Alkyl halides are compounds in which a halogen atom, it can be fluorine, chlorine, bromine or iodine, replaces a hydrogen atom of an alkane. For example, see, this one is an alkane, RH. Here, H is replaced by X. So, this is alkane and this one is alkyl halides. Now, what is aryl halides? In aryl halides, the halogen atom is attached directly to the aromatic ring or benzene ring. Now, this halogen derivatives, that is alkyl and aryl halides, may further be classified on the basis of number of halogen atoms present in their structure as mono, di, tri or polyhalogenated compounds. For example, chloromethane that we have studied is monohaloalkane. Dichloromethane is dihaloalkane. Trichloromethane, which is known as chloroform, is a trihaloalkane. And carbon tetrachloride is an example of tetrahaloalkane. Monohalogen compounds can further be based on the hybridization and nature of the carbon atom to which the halogen is directly attached. We will start with monohalogen compounds and let us see the classification of these monohalogen compounds based on the hybridization of carbon atom. Which carbon atom? The carbon atom that is attached directly to the halogen atom. So first let us discuss when carbon atom that is attached to the halogen atom is sp3 hybridized. So first one is alkyl halides. So in alkyl halides, all the halogen atoms are connected to the carbon atom which are sp3 hybridized. See this one. This carbon that is attached to Cl, this carbon is sp3 hybridized. This one also sp3 hybridized. And this carbon that is attached to this Cl is also sp3 hybridized. Now this alkyl halides can further be classified into 1 degree alkyl halide, 2 degree alkyl halide and 3 degree alkyl halide. What is 1 degree or primary alkyl halide? If the carbon atom that bears the halogen is directly attached to only one other carbon, then the carbon atom is said to be a primary carbon atom. And the alkyl halide is referred to as primary alkyl halide. Now this, what is secondary carbon and secondary alkyl halide? If the carbon atom that bears the halogen is itself attached to two other carbon atoms, then this carbon atom is referred to as 2-degree carbon, and this compound is referred to as secondary alkyl halide. Now, in 3-degree alkyl halide, this carbon that is attached to the halogen is connected to 3 other carbon. So this carbon is known as 3-degree carbon, and this alkyl halide is an example of 3-degree alkyl halide. So in all these 3 examples, the carbon that is attached to the halogen, they are all sp3 hybridized carbon. Now let us discuss about allylic halides. In this, the halogen atom is bonded to the carbon atom next to the carbon-carbon double bond. Here also, notice that this carbon that is attached to the halogen, this carbon is sp3 hybridized. Now, what about benzylic halides? In this, the halogen atom that is bonded to the carbon atom is attached directly to a benzene ring. But here also, the carbon atom to which the halogen atom is attached is sp3 hybridized. So, these are the 3 examples of alkyl halides or allylic halides or benzylic halides in which the carbon is sp3 hybridized. Which carbon? The carbon that is attached to the halogen. Now we will discuss those halogen compounds where carbon is sp2 hybridized. Which carbon? The carbon attached to the halogen. Our first example is vinylic halides. In vinylic halides, the halogen is directly attached to carbon-carbon double bonds. Aryl halides. In aryl halides, this halogen is directly attached to the benzene ring. Now say this carbon that is attached to the halogen, this carbon is sp2 hybridized. Now this carbon that is attached to the halogen, this carbon is also sp2 hybridized. Our next example is carbon is sp hybridized. The first one is bromoethine. See this Br, that is a halogen. This Br is connected to this carbon. And what about this carbon? This carbon is sp hybridized. See here also Br attached to this carbon, and the carbon is sp hybridized. Now we will discuss the methods of preparation of alkyl halides. Our first method is we are going to prepare alkyl halides from alkanes by direct halogenations. Alkanes react with chlorine or bromine in the presence of diffused sunlight to give alkyl halide and HX. Now see, this is an alkane and this is alkyl halide. Now in this alkane, the H atom is replaced by X atom, or the H atom of an alkane is substituted by a halogen atom in alkyl halides. So this is an example of substitution reactions. We have studied that halogenation of alkane is an example of free radical substitution reaction. Now let us see this example. Methane reacts with chlorine in the presence of diffuse sunlight to give methyl chloride and HCl. But this is not suitable for the lab preparation of methyl chloride. Why? What is the reason? This is because methane reacts with chlorine in the presence of diffuse sunlight to yield a mixture of products. What are the products? Methyl chloride, that is a monohalogen derivative, methylene chloride dihalogen derivative. This is chloroform, trichloromethane, and carbon tetrachloride, that is tetrachloromethane. So here we are getting a mixture of products and it is difficult for us to separate them. So it is not a very good method for the preparation of methyl chloride in the lab. But if a proper ratio of the halogen to the alkane is used, it is possible to suppress the process beyond monohalogenation. However, the process is not of much practical use in the laboratory. This method is used industrially to manufacture chlorinated methane. Now, iodination of alkane is reversible. This is because the HI formed in the reaction is a very good reducing agent and it reduces the alkyl halides formed to the alkane again. So in this case, an equilibrium is set between the alkane and the alkyl halide. However, the equilibrium can be shifted in the forward direction by using oxidizing agent like concentrated nitric acid, HiO3 or HiO4. Now this oxidizing agent, for example HiO3, oxidizes the HI into iodine. See this example. Methane reacts with iodine to give methyl iodide and HI. Now this HI is a strong reducing agent. So what it will do? It will reduce the CH3I that is formed to methane. So as a result of this, the reaction is becoming reversible. Now how we are going to stop the reversibility, or rather I should say how we are going to favor the forward direction. In that case, we will use oxidizing agent. In our case, we have used HiO3 as the oxidizing agent. So this HiO3 is oxidizing this HI that is formed into iodine. As a result, the reversibility of the reaction is disturbed and the forward reaction is favored. Now, fluorination. Direct fluorination of alkane is not possible due to its explosive reaction. It is carried out indirectly by heating a suitable alkyl halide with inorganic fluorides. For example, CH3CH2Cl plus Hg2F2 is when you are heating this mixture, we are getting what? CH3CH2F, ethyl fluoride plus Hg2Cl2. So this example is of halide exchange method. This is not direct halogenation. Now let us discuss the preparation of alkyl halides RX from alcohols. This is the most convenient and the most widely used method for the preparation of alkyl halides. This method involves the replacement of OH of an alcohol by the required halogen atom. So this conversion of alcohols to alkyl halides can be carried out by the following methods. The first method is by using hydrogen halides. When an alcohol is treated with a halogen acid in the presence of a dehydrating agent, the OH group of an alcohol is replaced by an halogen atom. The dehydrating agent removes water formed in the reaction and thus prevents the reverse reaction to occur. The reactivity of alcohols towards this reaction for a given halogen acid follows the following order: 3 degree alcohol, greater than 2 degree alcohol, greater than 1 degree alcohol. Now this reaction is an example of nucleophilic substitution reaction. See, OH, that is a nucleophile, so OH minus is replaced by Cl minus. So this is example of nucleophilic substitution reactions, since both OH minus and Cl minus, or rather X minus, are nucleophilic in nature. Since the order of stability of carbocation is 3 degree greater than 2 degree greater than 1 degree, so the order of reactivity of alcohol is 3 degree alcohol greater than 2 degree alcohol greater than 1 degree alcohol. The reactivity of halogen acids towards this reaction is Hi greater than HBr greater than HCl. Now let us discuss the next method, that is preparation of RCl from ROH using phosphorus halides. We can either use phosphorus pentahalides or phosphorus trihalides. See, this ROH is reacting with PCl5. This is phosphorus pentachloride to give RCl plus POCl3 plus HCl. Similarly, alcohol is reacting with PCl3 to give RCl. These phosphorus halides are prepared by treating red phosphorus and a halogen. The advantage of using phosphorus halides is that the reaction does not involve carbocation intermediate. So, this is free from any kind of rearrangement. Now let us discuss the third method, that is Darzin's process. So in this method, ROH, that is alcohol, is treated with SOCl2 in the presence of pyridine to get RCl, alkyl halide, that is alkyl chloride plus SO2 plus HCl. So chloroalkanes can be prepared by refluxing alcohols with thionyl chloride. This SOCl2 is thionyl chloride in the presence of pyridine. Now, this method is very important and it is preferred over the use of HCl or phosphorus chlorides because the other products that are formed in the reaction, that is SO2 and HCl, being gaseous in nature, escape out, leaving behind only the chloroalkane in almost pure state. That means there is no problem in separation. So let us take this example, conversion of ethyl alcohol to ethyl chloride. So you can convert ethyl alcohol to ethyl chloride by using either HCl in presence of a dehydrating agent, or PCl5 or PCl3, or we can also use SOCl2 in the presence of pyridine to get CH3, CH2Cl. So this is the methods of conversion of an alcohol to alkyl halide. So today we have discussed the two methods of preparation of alkyl halides. The first one is from alkanes and the second one is from alcohols. In our next class, we will discuss 3 more methods. Thank you.